for PhD and all presentation will be in English. I hope everyone understand. Okay. Dr. Yosuke will be the president of committee today. Please.
Okay, good afternoon, everyone. Today we have different teams exam in topic luminescence study on lanthanide P+ ion group in lithium borate graph for laser medium and inflation material application by Mr. Ekapol Kaewmuang. And we have committee input, invite committee Professor Dr. Pupon Tanta and Assistant Professor Dr. Putipon Limpic and Dr. Nasekita Jantima and Associate Dr. Dr. Kelpa and the last one me, Dr. Yakin Yuri. Okay, if presenter maybe okay, please start.
Good afternoon, everyone. My name is Ekapol Kaewmuang, PhD student. Today I will talk about my thesis for defense examination in the topic of luminescence study of lanthanide ions, though lithium borate glass for laser medium and synthesis material applications. My advisor is Associate Professor Dr. Jakapol Kaewmuang. My co-advisor is Dr. Nasekita Jantima and Assistant Professor Dr. Putipon Limpic. We start with the introduction section of this thesis. Nowadays, the photonic application become to have a big role in my life. The photonic device such as the fluorescent lamp, laser device, LED light sensor, and routers give us the comfort for the many activities, even in the specific work. Therefore, the material that we use as the photonic material is very important. I'm interested in the two types of the material for the scintillation detector application and laser application. Both applications need the solid-state photonic material, which have the strong luminescence dopant, and for the scintillation detector, we need the host that have the high radiation capture properties. While for the laser medium, we need a host that support the luminescence of the dopant. Therefore, we need to try out the dopant first and choose the lanthanide ion to use as the dopant, because when lanthanide ions were excited by the proper energy, such as the photon, electric current, or neutron, the Fourier transition of lanthanide ion is occurred, and it gives us the strong emission. We can get the sharp emission band from the lanthanide ions. And from the Joule-effect theory, the asymmetric environment surround the lanthanide ion in both matrix can enhance the Fourier transition, give us the best luminescence of the lanthanide ion. And for this thesis, I use 4 lanthanide ions to dope in my class. Start with the samarium ion, show the reddish orange emission. Dysprosium ion show the yellow or blue or white emission. Europium ion show the red emission, and neodymium show the strong emission in the NIR. That we can use the nonlinear optical material to have the lambda to be green emission. Start from the introduction about the host of my thesis. The host material, I'm interested in the lithium gadolinium borate crystal, because lithium, boron, and gadolinium isotope perform the high neutron capture cross section. So, at the first time, lithium gadolinium borate crystal, though which lanthanide ions were prepared and studied, but it found some disadvantage, because when neutron were captured by gadolinium, it emitted high energy gamma ray, and this material sensitive with the gamma ray background that produce from the neutron source. Therefore, next, these crystals were improved by change from the gadolinium to the yttrium. Lithium yttrium borate crystal, though which lanthanide ions perform the true properties about the neutron detection. Moreover, Moreover, when we look at the structure unit of the yttrium oxide of the hydrogen. Actually, it has the YOH. We found the two oxygen that exist. These two excess oxygen make the asymmetric structure occur in the octahedral unit and form the two-perfect theory. Lanthanide ion like the asymmetric structure because the asymmetric structure can improve and enhance the luminescence properties of the lanthanide ions. Therefore, lithium yttrium borate crystal were doped with neodymium, erbium, and yttrium to study for the laser application also. As I said, lithium yttrium borate crystal doped with lanthanide ions perform the interesting properties, but however, it is crystal material. And crystal material still have some disadvantage, such as once time you prepare the crystal, you can get just a small piece of the crystal, and it's hard to control the shape of the crystal. And the process to prepare the crystal is so complicated, can take a long time. And this makes the crystal have the high cost, result to the high price of the production from crystal. Therefore, we need to find out the optional material that can be used to replace the crystal in this device. Jackpot, we have the glass material. The glass material can be prepared in various sizes and shape and use the short time duration, maybe 1 or 2 days, to get the many numbers of samples of the glass sample. And we can control the shape easily more than crystal. And of course, glass material is cheaper than crystal. It is a challenge to prepare and study the lithium yttrium borate doped with lanthanide ion in glass form. This is my purpose of this thesis. I try to change from the chemical composition from the crystal form to glass system by conserving the preservate ratio. And then I know the dysprosium, samarium, europium, and neodymium oxides with different concentration to find the influence of the lanthanide ion concentration in the body's glass on the physical, optical, and luminescence properties. And second, I try to investigate the laser and scintillation potential of this glass also. This is my two purpose of this thesis. Next, move on to the experimental method. Start from the all process of this thesis. I prepare the glass by melt quenching technique. After that, I study the fundamental properties by calculate and measure the molecular weight, density, refractive index, and the thickness of the glass. I study the optical properties by absorption spectrum, investigate the luminescence property by emission and excitation spectrum and the decay curve. I try to study the scintillation properties of the glass by measure the X-ray luminescence spectrum. And finally, I try to study about the effect of the temperature or luminescence property of the glass by measure the temperature dependent luminescence spectrum. Next, I calculate and analyze about the molar volume and the concentration of the lanthanide oxide and the ion concentration of the lanthanide ions. And I take the emission spectrum to find out the emission current passed through the CID 1931 chromaticity. I take the sum value of the fundamental properties, absorption spectrum and emission spectrum to analyze the laser potential by using the Joule-Perfect analysis. The calculated lifetime and experimental lifetime on the decay curve were compared together to evaluate the quantum efficiency. And finally, I fixed the decay curve that show the non-single exponential, which the IS model to explain about the energy transfer process between the lanthanide ions. This is the glass production. Start from the wetting, put it into the crucible, and then melt at 1000 degrees Celsius for 3 hours, and then quench it at room temperature, and anneal at 300 Celsius degree for 3 hours, and finally we cut and polish to get the glass sample. This is the analysis instrument. We use the spectrophotometer for absorption spectra, fluorescence spectrophotometer for excitation emission spectra and decay curve. active refractometer for refractive index. Use the 4-digit sensitive microvarant for density measurement using the Archimedes principle. This is the experimental setup in the glass lab to measure the emission spectrum in the near infrared region of the ND doped glass. And this is the experimental setup here also to measure the X-ray induced luminescence spectra. And this is the experimental setup at the Korea National University to measure the temperature dependent luminescence. Next, I talk about some calculation and analysis method that important for this thesis. The first one is we measure the weight of the glass in air and in liquid such as the water, and we use the equation 1 to calculate the density. Next, we calculate the molar volume by using equation 2. This is the diagram of the two-phase analysis. We start from the used absorption spectrum to calculate the experimental air-scatter strength (FESP), and then we use the FESP to fit with this equation to get the F-cal calculated oscillator strength to get the omega 2, 4, and 6. Then omega 3, 4, and 6 pass this equation to find out the relative transition probability AR, and AR was used to evaluate the Tau-cal calculated lifetime and branching ratio, and finally we take this value with the emission spectrum data to get the final value sigma, the stimulated emission cross section. Because we have the many parameters in my thesis, I just talk about the important. Okay, just start with the omega 2. Omega 2 is tell us about the degree of the asymmetric environments around the lanthanide ions in the glass matrix. And it can also tell us about the degree of coherency between lanthanide ion and ligand. Omega 4 and 6 tell us about the degree of the viscosity and rigidity of the glass. Branching ratio show the emission ratio and lacing power from this glass. Sigma, stimulated emission cross section, give us about the laser threshold. It is the minimum energy used to start the lacing action. This is important. And it also tell us about the briefly about the output per input ratio energy. This value don't give us the exact value, it's just the approximation, and it just tell us about the degree when we compare with the other glass. Just tell us about the higher or lower when we compare with the other glass. Tau-cal is the relative lifetime of the luminescence from the two-phase analysis, and Tau-EXP we can measure directly from the spectrophotometer. This is the non-radiative transition analysis. I need to talk this topic because it relates with my result. The transition from the luminescence level separate into transition, two types of the transition. The first one is the radiative transition. It gives us about the light emitting, photo emission. And the second one is the non-radiative transition. The non-radiative transition consists of phonon vibration. It means this transition gives us the phonon vibration, gives us the OS vibration, gives us the concentration quenching, and gives us the cross relaxation and energy transfer. We like this one. We don't like this one because this one gives us the strong luminescence. And however, our glass have both transition. And the non-radiative transition rate is related with the experimental lifetime that we measure from the measurement. That means concentration quenching, cross relaxation, or energy transfer is effect to the our luminescence lifetime. Moreover, OS vibration and phonon vibration is also related with the quantum efficiency. You can see this related with the UNR and the UNR related with the quantum efficiency. That means phonon vibration also affect to the quantum efficiency. This affect to my work. Next is the Inoguchi-Hirayama-H model. When we measure the decay curve, the luminescence decay curve, if we found the non-single exponential, that means we need to fit the non-single exponential, which is this model, to find Q parameter. Q parameter is the energy transfer parameter that tells us about the probability of the energy transfer from one lanthanide ions to another one lanthanide ions. And from the fitting, if S from the fitting that we choose and show the base fit with our data, if S6 show the base fit, that means the energy transfer is the dipole-dipole interaction, and if S is A is the dipole-dipole interaction, and if S is 10 means quadrupole interaction. It's the interaction between the lanthanide ion in our class. And okay, I said this already. This is the equation and relation that I use to investigate the color of emission by this relation, and the value that I need is the small alphabet x and y. I will take x and y coordinate up to this diagram to find out the emission color that get out from my glass. This is the theory. And also I check with the UV lamp to confirm this color coordinate also. Next, I move on to the result section. Start with the glass sample. This is the DY dot glass and Samarium dot glass show the same outlook, light yellow and good transparency. Also with the European dot glass also show the light color and good transparent. But for the ND glass, when we dope neodymium oxide more and more into the glass, the color of the glass change from yellow to be the blue color. Just ND only. Now I move on to the density and molar volume of the glass. This is the all result about the density and molar volume of my glass. It show the same trend. That you can see trend. Please don't. We have some error value in the relation, but if we consider about the trend, density and molar volume tend to increase with increasing of lanthanide oxide concentration for both density and molar volume. About the density, we can say that because dysprosium, samarium, europium, and neodymium oxide is heavier than borate, and when we dope these more lanthanide ions, the borate is reduced. That means we replace with the heavier elements, and it makes the total molecular weight of the glass higher, and this makes the glass more dense. For the molar volume, the molar volume is increased with increasing of lanthanide oxide concentration. We can say that the lanthanide ion act as the modifiers, and modifiers destroy the oxygen bridging in the glass network, and it creates the space because some bonding is destroyed. It generates the space, more space, more volume. This is my explanation about the density and molar volume. Next, the reflexive index. I try to find the relation between the reflective index and the lanthanide oxide concentration, but not found a clear relation. So this is my opinion. Maybe the lanthanide ions is distributed in my glass with non-equality on the glass, not same. Maybe dense at the middle or maybe dense at the rear. This means the fluctuation value of the light velocity of the glass, and its effect to the not clear relation with the lanthanide oxide concentration between the refractive index and lanthanide oxide concentration, not clear relation. Okay, I move on to the spectroscopic result of the first series of the glass, divided glass. This is the absorption spectra of the divided glass. This portion absorbs the photon in visible light and near infrared region. And the most absorbed bands of this portion is about 388 nanometer. is overlapped with the host absorption about here. You can see some curve and some curve here. Moreover, the absorbance value is more and more. That means this glass can absorb more photons with increment of dysprosium ion in the glass. And we found the hypersensitive transition band at the 1284 nanometers. This is the hypersensitive that so sense with the asymmetric environment surround the lanthanide ions. If the lanthanide ions were surrounded with the asymmetric host matrix, this grow higher and higher and higher. Because of the most absorbed band is belong to 388 nanometer, I choose this wavelength to excite the glass for study the emission spectra. We found the 3 emission band and the strongest emission is 575 nanometers. The transition occurs from the luminescent level OF9/2. And the emission intensity increase with increasing of dysprosium oxide concentration from 0.5 to 1%. But for the 1.5%, the intensity is dropped because of the concentration quenching effect. Moreover, the strongest one is the peak from the electric dipole transition, and the left one is the magnetic dipole transition. The electric dipole transition is supported and enhanced by the asymmetric environment surrounding the dysprosium ion. If EDP is higher than MDP, this is a confirmation about the asymmetric environment surround the lanthanide ion in the glass. To confirm the excitation wavelengths, I measured the excitation spectrum and found the strongest excitation at 388 nanometer. This result is corresponding with the emission spectra. I took the emission spectra to calculate the color coordinate by the CIE1931 and found that color coordinate is plotted in the white region. That means in theory, the white glass perform the white light emission. It's confirmed by UV lamp excitation. You can see this is the real one. The real picture that the white glass perform the strong white light emitting. Decay curve for measure with the fluorescence spectrophotometer. The first one, I fit the decay curve with the first E for the exponential decay and get the experimental luminescent lifetime in the millisecond. And however, I still found a non-single exponential behavior decay. These 3 lines, the blue, green, and pink, is the non-single exponential. So I fit it with the IS model to find out the Q parameter. The Q parameter tells us about the strength of the energy transfer. And the Q value is increased with increasing of dysprosium oxide concentration from 0.5 to 1.5. This means more dysprosium ion. The dysprosium ion more get close together and easy to energy transfer. For fitting, the best fit occurs when I use the S is 6. That means the energy transfer is occurred by dipole-dipole interaction between the dysprosium ion. Next, I move on to the Jude-Offset analysis. The first step of Jude-Offset analysis gives us the omega 2, omega 4, and omega 6 value. Then I take this value to compare with the photon glass from the literature and found that the omega 2 value is higher than half of glass in the table. That means this dysprosium ion in my glass have the asymmetricity of the environment higher than the half of glass in the table. For the omega 4 and omega 6 also, omega 4 and omega 6 is higher than half of glass in the table. That means my glass show more viscosity and liquidity than half of glass in the table. Just comparable. The next step of the Jude-Offset analysis gives us the sigma and branching ratio. If we compare between just three emission wavelengths. The emission wavelength that good for use in the laser is 575 nanometers because the sigma value is the highest compared with photon wavelength. That means this wavelength use the lowest energy to start the lasing action. And the branching ratio of this wavelength also the highest. That means this wavelength perform the highest lasing power for the this glass. However, when we compare this value with the outer glass, my glass is not good because the sigma and quantum efficiency is low. That means when compared with the outer glass, my glass needs higher energy to start the laser process than outer glass because of the asymmetric level surround the dysprosium ion in our glass is still not high. And when we consider about the quantum efficiency, it's also low because of the high phonon energy in my glass and because of the OH group in my glass also. This reduces the quantum efficiency. Next, I move to the X-ray induced luminescence. We found that the X-ray induced luminescence shows the same pattern of the spectrum, similar with the photoluminescence that I presented to you before. Nothing changed, just small shift of the peak, but the quenching and the pattern of the peak is same. Next, this is the temperature-dependent luminescence. We just found just two peaks of the dysprosium ion because the weak signal. And the intensity of the luminescence decreased with increasing of the temperature. Because when the temperature is higher, the number of photons is increased. The number of photons increased, the non-radiative transition rate is increased. And I told you before, it compares between radiative transition and non-radiative transition. If NR is high, luminescence is low, not bad. Bad. This is the finish for the DY glass. Next, move to the SM glass, and I will talk faster because some discussion is same with the dysprosium ion. Start from the absorption spectrum. This SM glass absorbs photons in visible light and NIR region, and the most absorbed band is belong to 403 nanometers. I took the most absorbed band to excite the glass for the emission spectrum. Perform the strongest emission at 600 nanometers from the luminescence level 45/2. And we found the concentration quenching effect that showed the highest intensity for the 0.5% low glass. Next, to confirm the excitation wavelengths, I measure the excitation spectra and it corresponds with the emission spectra that show the strongest excitation at the 403 nanometer. I take the emission spectra to color coordinate evaluation, and the color coordinate is on the orange region. That means in theory, this gas perform the orange emission, and I confirm by exact picture which the UV lamp excitation it show the exact orange color when we excite it with the UV lamp. Decay curve. The first one is I measure the lifetime and found the lifetime of this gas is in the millisecond or so. And the lifetime decrease with increasing of the samarium oxide concentration combined with the non-single exponential in the decay curve. I fit it with the IH model and found Q is increased with increment of samarium oxide in the glass matrix. That means more samarium oxide easier to energy transfer and it dropped down the luminescent lifetime in the glass. Also, for fitting, the S show the test fit at 6. That means the energy transfer is a type of dipole interaction between the samarium ion. Next, JO analysis. First step about we get the omega 2, 4, and 6, compare with other. And when we compare, it shows that our glass show omega 2, 4, and 6 lower than most of glass in the table. That means the asymmetric level of our glass surround the samarium ion is lower than most of glass in the table. Also with the lower viscosity and rigidity.
The second step, we get the sigma and the beta, but we have the conflict between the sigma and beta value. From the discussion, we can say that if you want to take this class for the low energy consumption laser, we need to use the 646 nanometer. But if we want the high power laser, we need to use the 600 nanometer because it shows the higher beta. Higher beta means higher power laser. Higher sigma means the lower in the laser threshold, the minimum energy that start the laser action. However, I need to choose one to compare with the outer glass, so I choose this 600 because in the emission peak, it shows the strongest emission peak for the 600. And of course, when compared with the outer glass, my glass is not good. Even in the energy that used to start the lasing action need high back orders because of the asymmetric level is low, and the quantum efficiency is also low compared with the outer glass because of high photon energy and lowest vibration in our glass. Next, X-ray luminescence and show the same pattern with the photoluminescent emission spectra. The difference is the quenching because for the X-ray luminescence, the quenching occurs in the SM with the 1.5 mole percent. For the temperature dependent luminescence, we found some emission peak similar with the photoluminescent emission spectra and give the same reason about the luminescent intensity decrease with increment of temperature. It is due to the photon increasing. Now I move on to the third series of the glass, EUO glass. Absorption spectrum show the absorption of the photon in visible light and near-infrared region. The best absorbance occur at the 394 nanometer. Through this wavelength to excite the glass for studying the emission spectrum. Found for emission, the strongest emission is located at 613 nanometer. This transition comes from the luminescence level 5D0. The emission intensity show the highest for the 4% low glass. This comes from the concentration quenching effect. To confirm the excitation wavelength, I measure the excitation spectra. It corresponds with the emission spectra, but however, we found a small photon five band here. This is the amplification about the X200. This photon sideband occurs